Good day, everyone. On behalf of Cambridge Health Tech Institute's Global Web Symposia Series and our sponsor, Wyatt Technology Corp., I'd like to welcome you to Advances in High-Throughput Screening of Aggregation, Stability, and Viscosity, utilizing light scattering in microwell plates. My name is Elizabeth Lamb, and I'm the host and the technical director for today's event. I'd like to introduce our presenter for today. He is Daniel Sohm, Principal Scientist for Wyatt Technology Corporation. Welcome, Dr. Sohm. The presenter ball is yours.
Thank you, Elizabeth, for that introduction. Now, it's critical to apply the right analytical tools at each stage of R&D, by which I mean those instruments that can answer the questions or meet the analytical challenges presented at each stage. Light scattering is one of the primary means for doing so, and in fact, Wyatt Technology offers a suite of analytical tools, all based on light scattering, that do meet these needs. Now, when Discovery sends down small quantities of candidates, multiple candidates for evaluation and ranking, we'll need to make sure that we're on the right track. So we need to screen through many different clones, buffer conditions, etc., find the most promising. And light scattering helps to determine the essential solution properties, such as molecular weight and size, quality and stability indicators, such as degree of aggregation, aggregation rate, propensity for aggregation, including colloidal and thermal stability, solubility, and also the viscosity of concentrated protein solutions. After having narrowed the field of possible candidates or buffers, we then go on to test a smaller number of samples under accelerated stresses such as freeze-thaw or stirring, shaking, elevated temperatures, and then further reduce the number of samples for long-term shelf life stability studies. Here, light scattering can verify important properties such as the integrity of the drug candidate and identify and quantify degradants such as aggregates or fragments. It can also highlight subtle modifications to the molecule that will show up through their protein-protein interactions or perhaps in their overall net charge. Finally, as we go through iterations of the R&D cycle, it's important to go back and understand what made a particular molecule or buffer fail or succeed. In the context of aggregation or viscosity, that usually means analyzing the intermolecular interactions, such as excipient protein binding, interactions between co-solutes in a cocktail of antigens or a cocktail of therapeutic monoclonals, their self-association, and also the molecular charge or zeta potential that contribute to these interactions as well. So the solution to all of these questions is light, or more accurately, light scattering. Today, we'll be focusing on question number 1, and I'll be presenting a single platform for carrying out all of these measurements. Now, you may be familiar with the DynaPro Plate Reader 2, which has become well established in the biopharmaceutical field for screening proteins with dynamic light scattering, or DLS. Just recently, Wyatt Technology launched the DynaPro Plate Reader 3, which is the latest generation in this product line. It's a really exciting product. And the Plate Reader 3 adds new capabilities for measuring static light scattering, SLS, as well as DLS. So the addition of SLS means that it covers a larger set of biophysical attributes related to molar mass. And these are the gold circles in the figure here. So in addition to size distributions, colloidal stability via the diffusion interaction parameter Kd, thermal stability via the size aggregation rate, and the onset temperatures for size increase, that's T onset, and melting temperature, Tm, the DynaPro Plate Reader now determines molar mass, second viral coefficient A2 for colloidal stability, and the onset temperature for aggregation, Tag, for thermal stability. The aggregation rate is actually quantified simultaneously by measurements of size and molar mass, so you can get a nice picture in terms of which aggregates form and their conformation and extent. As in the previous model, that DynaPro incorporates a built-in camera that photographs the bottom of each well, so you can check if there was precipitation, formation of crystals, if there was a turbidity induced by going beyond the solubility limit, or perhaps bubbles formed, and you can go in and see perhaps why you got a funny looking autocorrelation function. So together with the solution properties, these images provide a comprehensive picture of the behavior of your samples. So what can we measure with light scattering? There are three essential flavors of analytical light scattering, and the first is static light scattering, or SLS. SLS can measure from first principles the molar mass of a molecule in solution, and hence help to identify a protein and determine its oligomeric or aggregated state. You can also analyze glycosylation. With multi-angle light scattering, or MALS, we can also measure the size of a particle in terms of its root mean square radius. By measuring how the solution molar mass changes with concentration or composition, we can also analyze interactions, protein-protein interactions in particular, to determine the equilibrium dissociation constant for specific interactions, or the second virial coefficient, A2, for nonspecific interactions. Dynamic light scattering takes advantage of the rapid fluctuations in scattered intensity that arise due to diffusion under Brownian motion. So by measuring the rate of fluctuations, we can determine the diffusion coefficient, and that in turn can be converted to a measure of size, the hydrodynamic radius RH. Measuring the diffusion coefficient versus concentration will allow us then to calculate another indicator of nonspecific protein-protein interactions, the diffusion interaction parameter KD. Now, phase analysis light scattering determines electrophoretic mobility, so also zeta potential and net charge of a molecule or a particle, but we won't be discussing phase analysis light scattering today. To learn more about light scattering and its analytical applications for characterizing macromolecules and nanoparticles, I would recommend visiting these pages on the Wyatt website. So a quick word about the analyses that may be carried out by DLS. When the solution contains a particle of a single size, DLS does a great job of determining its average radius. And if we carry out a distribution analysis, we'll see a narrow peak such as this one. If the solution contains a population with a small range of sizes, for example, monomers, dimers, and trimers, then DLS will not be able to resolve the unfractionated species, but will show a single peak that has been broadened. The width of the peak is presented as the polydispersity, or %PD. However, if there are populations present that cluster around average sizes which differ by a factor of at least 3 to 5 times in radius, DLS can resolve these peaks, and we call this a multimodal distribution. Each peak or each mode will have its own polydispersity representing the range of sizes within that population. So in the context of proteins, this might mean a main peak with a monomer, dimer, and trimer, and a secondary peak arising from large aggregates. Static light scattering will determine molar mass, and it provides the weight average molar mass. So if we're not doing a separation as we do in SEC moles, then basically we're getting what's known as a weight average molar mass of all the species present in solution. It is a first principles measurement. We determine the concentration independently, input that to the software, and combined with the scattered intensity, we will get the weight average molar mass. Static light scattering is really sensitive to aggregates. So if you're looking for those few fairly large aggregates, they're going to show up immediately in static light scattering. Or if there are lower levels of small aggregates, those will also lead to a change in molecular weight that we can see with the SLS measurement. The combination of static light scattering and dynamic light scattering will help discriminate between unfolding and aggregation. So we have a change in size that we see by DLS, but no change in molecular weight as determined by SLS. That indicates a pure unfolding phenomena. On the other hand, if the molecular weight does increase, and then we have a direct indication that there's not just unfolding, but also aggregation. So because we're not doing a separation here, the determination of molecular weight that we get by in-plate SLS is not as accurate, not as quantitative as if you were to do a full SEC moles measurement. But there's really great uniformity between wells and across similar plates. So you make the measurement of neighboring solutions, and you'll get a good indication of their behavior, especially in a relative manner, one to the other. So how do we measure the dynamic light scattering and static light scattering in the plate? Here's a view into the DynaPro plate reader, and we can say that we use standard plates and illuminate from below with a laser beam. The scattered light then comes back out the bottom of the plate, and it goes into an avalanche photodiode. Now, most common avalanche photodiodes are great for the rapid high-speed measurements that are needed to make dynamic light scattering analyses, but they're usually not, they don't have the linearity that's needed to make an effective static light scattering measurement. So in the Plate Reader 3, we've introduced a new linearized avalanche photodiode, which has an extended range for linearity and helps us get accurate molecular weights over a pretty good range. The benefits of making DLS measurements in a plate, or making actually any measurements in a plate, is that there's no additional sample handling. You load them in and it doesn't have to be sampled out with a needle, injected into some other instrument, or somehow loaded and undergo additional handling. It uses standard Microwell plates, so the same Microwell plates that you use for multimode plate readers will work here. And the sample volumes can be very low, as low as 4 microliters per sample in a 1536 well plate. Or if you go to the larger well plates, even up to 150 or 200 microliters, if you want to use that sample for multiple measurements. For instance, first measure dynamic light scattering, then move that plate over to an SEC sampler, or move it over to a microimaging system to sample out some of the material and see what else you have there. So it's very versatile and can be utilized in various stages of development. And of course, it integrates with the entire plate-based ecosystem. So you can integrate this with robotics. You can manually or automatically transfer the plate into the plate reader, move it into a storage facility, move it into a different product, and back and forth. And so it works with your plate-based workflow. So the DynaPro Plate Reader 3 is the newest instrument in the DynaPro Plate Reader product line. It continues to use standard 96, 384, and 1536 well plates of the type that you are probably using in your other plate readers, whether from Grainer, Corning, or Aurora. You'll notice that it has a really beautiful new front panel display, which makes it easier to get at some of the key information that you need at a glance. The range for size is 0.5 to 1,000 nanometers in RH, and the range for molecular weight is a kilodalton up to a megadalton. The sensitivity for hydrodynamic radius is comparable to measurements in cuvettes, so it's 12.5 micrograms per milliliter of IgG. And the sensitivity for molecular weight is not quite as good, so it is relatively challenging to make excellent SLS measurements in a plate at the level that you might be used to from SEC mols. So the lower limit here is about 1 mg per mil of BSA, which works out to approximately 0.4 mg per mil of IgG. Temperature control, you can bring it down to low temperatures and do long-term stability at 4 degrees Celsius. You can do temperature ramps up to 85. You can do isothermal and all the range up to 85 as well. There is a new evaporation control system in this Plate Reader 3, and so you can cap the wells with oil, and that has certain advantages. But when that doesn't work, you are welcome to seal it with a tape, and whereas in the past there had been a limitation of condensation forming on the tape, which introduced some degradation of dynamic light scattering signal. In the Plate Reader 3, we have an element that eliminates the condensation on the tape, and so that is a convenient way to control evaporation as well, whether it's for a long-term measurement or for elevated temperatures. The DynaPro offers an API for control of the instrument and data retrieval. So again, if you want to integrate it with your existing plate-based robotics, that will work. And it integrates a camera which images the bottom of each well to look at precipitation, formation of bubbles, whether it's to determine what else is going on in your sample, or to go back and do a diagnostics and see why perhaps you got a funny looking autocorrelation function. The benefits of making measurements in a plate is, first of all, it's non-perturbing. So there is no sample handling. It's not being sampled out and run through tubing somewhere else, sent back into the plate. Everything happens right in the plate. And because the DynaPro plate reader uses a long wavelength laser at 830 nanometers, there's no exposure to ultraviolet light. Now, you may wonder why that's a concern, but of course, it's been established that there is a risk of ultraviolet light causing aggregation in proteins, and especially drastically for ADCs, antibody-drug conjugates. So some of the other techniques that you may be using to assess stability and aggregation might use ultraviolet light, and there is a concern about it causing aggregation, but that doesn't happen in the DynaPro. Because you can use 384 and 1536 well plates, it's easy to add in triplicate measurements of everything that you need to measure. Controls as well, so you can measure the samples at various concentrations, the pure buffers, and go through the statistical replicates that are needed in order to validate your data. You can make the measurements directly in the well plates and then transfer those plates as is without perturbation to another instrument. And there is a full degree of automation in the software that allows you to program a complete multi-sample, multi-temperature protocol, then pop the plate into the instrument and just walk away, come back when it's done. Everything will be available for you. And the dynamic software, which operates this instrument and does the data analysis, will show you at a glance what the results of your plate look like. If you're interested in more information, again, I encourage you to visit our website. The plate reader, wyatt.com/plate reader, introduces the plate reader 3 and is a good overview of what it can offer you. So there are many, many applications of dynamic light scattering in well plates for various areas of drug discovery, nanoparticles, protein R&D. Today I'm going to focus on biologics development, and in particular applications of the in-plate DLS to protein aggregation, look at size and distributions, molecular weight, the rate of aggregation, the colloidal stability parameters, the thermal stability parameters, assessing the interaction behavior around the structural changes. So if you have an unfolding event or some other structural change, how does it impact the protein-protein interactions? Measurements of viscosity and solubility. Here's a nice example of looking at aggregation in a 96 well plate. So this was a relatively low volume screen. It did use more sample than some of the larger well plates might use, but it only took 45 minutes to run through all of these. And so the results are color-coded. Red indicates monodisperse or low aggregation, as you can see up here, a really sharp peak at 3.5 nanometers. The blue indicates those that are more polydisperse, and so here we have mixed in some 100 nanometer particles, and then the black ones are those that we can basically discard. There's been significant precipitation, and we have no interest in proceeding with those formulations at all. So imagine that you had a 384 well plate now. Well, you could populate that with 5 candidates, each at 5 different pH values, each of those at 5 different ionic strengths, and each of those across 3 replicates, and add in 9 controls, buffer or something else, and all of this can be scanned in less than 1.5 hours to determine polydispersity, which essentially tells us about the presence of small aggregates, as well as the presence of large aggregates, like the population we see over here. So with the addition of the new capabilities of the DynaPro Plate Reader 3, we can measure molar mass across the entire plate. And so you can see here the result of a screen of 2 different MABs, A and B, in 6 different formulation buffers. There were also some wells which were used to measure just the buffer. And this is a concentration series. Okay, so basically changing concentration from 1 to 10 mg per mil with 2 replicates at each of those concentrations. And there's a complete scan. Some of these were out of range. That's the black, and the others span the range from between about 130 to about 300 kilodaltons. Simultaneously, we're measuring size, so the same wells we're also measuring size, and here are the results for those as well. And if you so choose, you can display color coding of the polydispersity as well. So this is a really nice way to get a quick overview of which buffers and which concentrations are appropriate. You'll notice that there's some empty wells here, and that's because the software allows you to do some programmable filtering based on data quality. So based on the various types of algorithms that are included in the software, you can say, well, there's a problem with the data here. There's probably a chunk of dust or something else in that well, so let's not take that measurement. And those are what you see here in the empty circles. And then the final results for all these measurements, whether it's molar mass, radius, polydispersity, and everything else that is analyzed, as well as the conditions of what's in each well, can all be exported into a spreadsheet format so that you can combine that information with information from other analysis techniques in your statistical analysis software or graphing software. And then once you have that information, then you can do a deep dive and look at those few wells which look the most promising. Of course, not all the ones displayed here are very promising. Some of them are highly aggregated. But here, this is another view that you can get just by going into the various wells and overlaying the information to look at the behavior under different conditions. Colloidal stability analysis, which is made through the concentration dependence of either the molar mass or the hydrodynamic radius, is perhaps one of the most critical and useful predictors of long-term stability because it really does indicate directly the protein-protein interactions that lead to aggregation. And so the plate reader 3 gives us the ability to measure both A2 and KD. A2 is the second virial coefficient measured with static light scattering, and its pure thermodynamic quantity that describes the protein-protein interactions as mediated by the solvent. Whereas KD, measured by DLS, is a little bit easier to measure. We did it in the previous version of the plate reader, but it's not quite as pure. It does incorporate certain hydrodynamic quantities as well as the thermodynamic interactions. A2 and KD are closely correlated, and that's why in the past it's been good enough to measure just KD. Early theory predicted that KD would be equal to something like twice A2M minus some factor multiplying the excluded volume minus an additional friction concentration coefficient. And we'll see later that this is close but no cigar. There are better analyses than the kind of earlier ones. The great thing is that both of these can be measured with high throughput. So using the plate reader, we can measure both of them simultaneously, and really where the see deviation from the expected relationship between KD and A2, perhaps learn something really interesting. In 2014, Menza and Fries published a paper which included a compilation of various publications in terms of the relationship measured between KD and A2, and found that almost all of the measurements were closely correlated by this single line described in the equation here. KD empirically is 1.2 A2M minus 6.3. And that was a pretty robust relationship. You can see that there's some outliers that were not included in the analysis, but it did differ from the theoretical relationship that I showed you in the previous slide. And so interestingly enough, in the same year, Dorota Roberts and her colleagues published a really detailed theoretical analysis looking at all of the possible contributions that are needed to determine KD theoretically based on the intermolecular potentials, and came up with a result of the final relationship of KD is 1.02 A2M minus 6.2. So I think that's really an amazing analysis that really delved deep into the theory, looked at every important contribution that goes into this relationship, and came up with something which was really amazingly close to the empirical relationship that was published right about the same time. So I think we now have, thanks to Roberts and colleagues, we have a much better understanding of the underlying processes that lead to KD, and we can rely on it at least for most IgGs. I think the outliers are probably more interesting in that if we do find an outlier that does not have the same relationship between A2 and KD, it will perhaps indicate something interesting going on in terms of the protein-protein interactions that do not fall within the usual interactions. So KD, as I mentioned, really correlates well to long-term stability because it does measure the interactions that lead to aggregation, and it can measure them under conditions which are relevant to the long-term stability studies. So measuring at the storage temperature, 4 degrees or 8 degrees, or measuring at room temperature. And so I have 2 examples here for that. On the left, what we see is a result published by Feng He and his colleagues at Amgen in 2011, which looked at the relationship between KD and long-term stability as determined by the formation of subvisible particles larger than about 2 microns. And they found that there's a threshold for their particular IgG. Above 8 milliliters per gram, the molecule is perfectly stable, and below 8 milliliters per gram, we can see the formation of aggregates. So that's one way of looking at the relationship and the importance of KD. On the right side here, we see a result published by Zidar and his colleagues in 2017, which shows the interaction of, the relationship of KD, shown on the horizontal axis, to the rate of aggregation, shown on the vertical axis. And here we can see a really fantastic correlation between them. They really do go well together. And so KD has been shown to be a really good predictor of long-term stability. Here's just some results of the measurements. So I showed you what happened in the plate and some of the results for molecular weight and size. By plotting those as a function of concentration, we can map out for all of the different wells in the plate, KD and A2. So a single 384 well plate will give you 10 concentrations for each buffer formulation, with 2 replicates for each of those concentrations across 16 different formulations. And in addition, you can put in pure buffer, which is needed to determine static light scattering offsets for this analysis as well. So one plate, lots of information. And this is a result from another article published by Dorota Roberts and her colleagues back in 2015. And again, how can KD be utilized to understand the protein-protein interactions? So what they did was took a few different buffers, which had different ions. So the key counter ion here varied, and determining the change of the protein-protein interactions across a series of ionic strengths. So one notable effect is that for most of the buffers, by the time you get to about 250 or 275 millimolar ionic strength, you've completely screened out that electric double layer, which gives you some net repulsion between the particles due to charge-charge interaction, and are left with only whatever's left over. So basically hydrophobic and other interactions that are non-electrostatic in nature. And they all collapse to about the same value of KD, regardless of which buffer is used, except for one buffer which contained sodium thiocyanate. And there, the sodium thiocyanate ion actually bound to the protein, presumably induced additional protein-protein interactions. We can see that for most of the buffers, as you go to lower ionic strength, there will be an increase in the intermolecular repulsion, which we see as an increase in the value of KD. And that's not surprising because you're basically less and less screening the intermolecular charge, the net charge that causes repulsion. But for one buffer, the citrate buffer, there's actually an increase in attraction as you go to lower ionic strength. And so their speculation was that there's a surface charge inversion due to binding of the citrate on the molecule. KD is also useful for predicting viscosity at high concentrations. So when you're early on in the development process and only have very little material to work with, don't want to go to one of those cone and plate measurements and want to screen a large variety of conditions in a short time, you can use the DynaPro plate reader, and the way that it turns out that KD will predict the viscosity at high concentrations. So what we see here is a series of formulations or monoclonal antibodies. And we see a really nice correlation between KD, which is the black bars, and the viscosity. So the higher the KD, the lower the viscosity at high concentrations. And then those that have negative values of KD down here, you see that we have some pretty high values of viscosity. And so this is a nice predictor. And interestingly enough, it doesn't take very much to flip the behavior. A single charge flip mutant, shown here, can easily vary the behavior between repulsive and low viscosity to attractive and high viscosity. So here are the attractive KDs with their corresponding high viscosities. This is a really great way to screen through lots of different candidates and mutants and formulations. And this material was taken from a paper published by Connolly and colleagues in 2012. So moving on now to from colloidal stability to thermal stability. The DynaPro is great for doing in-plate accelerated aggregation studies. You can let the entire plate sit there at 40 degrees or 50 degrees or whatever your preferred elevated temperature is, and look at the change with time of the overall molecular weight and size. And you can even use it for longer term aggregation studies where you take the plate, put it into a stability chamber, do whatever it needs to do there, whether it's some freeze thaw or stress or long-term aggregation. Periodically move it back in, do a quick scan to get all those values of molecular weight and size, and then move it back for the next stage in the stress. You can also do temperature ramps to look at the onset temperatures. So we utilize T-onset to signify a change in size measured by dynamic light scattering, and T-aggregation to indicate a change in molecular weight using static light scattering. And so we can measure these simultaneously. That's shown in the upper graph. And so here you have the value of T-onset and the value of T-ag for this particular monoclonal antibody. We can also measure the melting temperature, the midpoint of the melting temperature for some protein. So if the protein is not aggregating, but it remains monomeric, the static light scattering will tell us that because the molar mass does not change. And then we can determine the midpoint for that unfolding process, which is Tm. Another nice thing we can do is measure the changes of the colloidal interaction with temperature. So how does Kd or A2 change with temperature? In the course of those elevated temperature measurements, we need to do something to control evaporation. So in the past, we have always had the option of using an oil cap, which is, for many people, that's quite convenient. It gives you a nice smooth optical interface, gives pretty good data. And we've added into the DynaPro Plate Reader 3 the option of utilizing standard sealing tape, which can be much more convenient. Oil may not be useful if you have some surfactants in your formulations, because of course that will cause the oil to dissolve into the formulation, so that's a good idea. In those conditions, we can use sealing tape. And we have a heater above the plate, which raises the temperature of the tape by a couple of degrees, and that prevents condensation. Condensation is bad for light scattering because the drops can scatter a lot of light. And so now we have this option where there is no impact on optical performance. You can make the measurements at room temperature without the evaporation control, or with either of these evaporation control options, and at elevated temperature with these options, and they all give you really great data. So here's an example of an isothermal study published by Skamras and his colleagues in 2016. And it shows the aggregation analysis over time courses of 20 hours for 3 different IgGs. And these proteins have undergone different stresses of acidification, neutralization. And the different behaviors that we see through the change in RH are indicative of different aggregation pathways or mechanisms. So These data were taken before the DynaPro had the molecular weight option. Now with the addition of molecular weight, we can get even more information about the types of aggregates that form under each of these different stresses. Here's a measurement that we did, and it shows the NIST standard monoclonal antibody, and boy, is it stable. Keep it at 40 degrees over a couple days, and it does not change in size. It does not aggregate, it does not fold. It's a really stable standard. So it's been a valuable addition, I think, to the toolkit of anybody who needs to validate their instrumentation. The NIST standard is really something to look at if you haven't yet. Here's another way of presenting a time course. Since we are making measurements in plates and we do have so much information available, it's nice to be able to generate a visualization of the entire time course. And so these data were provided by Xiaoxi, and it's not for proteins. In this case, it's actually for nanoparticles, but it does show an aggregation time course of multiple species in multiple media over a course of several hours at different concentrations. So you can see the entire set of concentrations running down here, the different media that were used here, and then time courses here, and it's all color coded, gives you a fantastic visualization. Here's a measurement we did of three IgGs an IgG in 3 different formulations, looking simultaneously at changes in molecular weight and radius. And so the red plots correspond to the same condition. So at pH 4, we can see that the molecular weight goes off the chart at about 55 degrees, and then the RH goes off the chart a little bit later. And similar for pH 6 with 150 millimolar sodium chloride. And then something different is happening in histidine. You can see that there's a region here where there's a change in size from about 5 to 10 nanometers in radius, and there's an increase in molecular weight from 150 to about 350, 400. So this would be indicative of the formation of stable aggregates at this temperature, and only when you get to a secondary condition at about 75 degrees do things start going off the charts, and there's major aggregation going on. So lots of information, again, that we can get here by combining SLS with the quantitative SLS with DLS. I mentioned that KD correlates really well with long-term stability. Here's another graph from the same paper by Zidar and his colleagues, looking at the correlation of the thermal stability parameter. In this case, it was TM determined by DSC and by DSF. We essentially determined very similar temperatures using T-onset and dynamic light scattering. And the correlation is not so great, as you can see. So within a given formulation, given molecule, there are definitely some nice correlations. But overall, across the two different MABs that were studied here, MAB 1 and MAB 2, it's only a partial correlation. This is true in another study, which was published by Chowdhury and his colleagues in 2014. And this was a fusion protein between serum albumin and its partner SEPHB4. And so the SEPHB4 domain does actually have a really nice correlation between different formulations that give different melting temperatures and the rate of aggregation. But the HSA had essentially no correlation. So again, the TM, in my opinion, is not really as good as KD, though it is important for understanding stability, but it's really not as great for predicting long-term aggregation. Nevertheless, it can be done in the plate reader as well, and there may be some additional information that you can get using dynamic light scattering and static light scattering to determine the colloidal stability as a function of temperature. So here's an example of an IgG, and in black, we have RH as a function of temperature, and so you can see that it undergoes a transition right around here. And the red is the SLS, so that's essentially the aggregation, and it has a very similar aggregation temperature. It also aggregates about the same time, perhaps a little bit later, slightly later in temperature. If we look at KD here, which is the diffusion interaction parameter, tells us about colloidal stability, we can see that it actually takes off and starts increasing. The repulsion, the attraction between molecules starts increasing. So lower KD is going to a higher, more negative value, is an indication of increase in attraction. And that increase in attraction begins much earlier. So let's zoom in a little bit on the graph. And we can see that the change in KD begins at about 52 degrees, while the change in RH and SLS begin about 55, 56 degrees. So clearly something is happening here, which is not really showing up in the measures of size and aggregation. It's a small change in the molecule in terms of conformation, but it is changing the interactions between the molecules. So perhaps barely exposing a hotspot for aggregation. As that's being exposed, is starting to lead to some additional attraction. And only as you go to higher temperature does that actually show up. So well, I think this needs to be studied a little bit more. I do think that the onset temperature for interactions could be a better predictor for stability, as for thermal stability, than just looking at RH or SLS. And this was articulated well by Mentz and Fries in 2014. They provided a survey of various techniques for assessing stability in formulation development. And we can see that they're in fact quite fond of DLS, shown here both with and without temperature ramps, to measure KD at room temperature, KD as a function of temperature, and also RH as a function of temperature. And they also put in UV vis, which essentially is SLS. So in the DynaPro Plate Reader 3, this is what we would call the SLS measurement for measuring TAG as well. And these are all considered essential for formulation development. And in particular, it was their opinion that the KD versus temperature is a remarkable measure of formulation properties and stability. So I think this is something which will be really nice to look at in more detail, and perhaps we can get some more publications which disseminate this information to the public. I mentioned viscosity, and viscosity in particular of concentrated protein solutions, of course, a very important parameter for injectability and being able to just process viscous solutions of concentrated proteins. And DLS can make viscosity measurements. It requires only 10 to 20 microliters per well of sample. In fact, I'm sure that we can do it in 5 microliters as well using the 1536 well plate. And we do it by inserting a probe. That probe is essentially a bead, such as a polystyrene latex bead. I've also heard that people have been really successful with PEG-coated gold nanoparticles, as long as they're well characterized. So we've used dynamic light scattering to characterize them in standard solutions, determined their hydrodynamic radius. Typically, we use beads with radii between 50 and 250 nanometers. And using the Einstein-Stokes equation, we can isolate the viscosity of a solution by measuring its diffusion coefficient and the known RH and the temperature. Together, these will provide viscosity. And so Fenghead and his colleagues at Amgen published this a while ago, back in 2010, showing that there's a really good correlation between measurements of viscosity for concentrated proteins using standard viscometry or dynamic light scattering. The inset shows here shows the apparent change in size of the bead as the viscosity varies between low viscosity here and high viscosity here. And so these are beads of the same size, but the shift in the apparent radius is a result of the viscosity, and that's analyzed to determine the viscosity, not of the buffer, but of the entire solution which contains the proteins. We can also use the DynaPro to measure turbidance. And so typically turbidance is measured using either static light scattering or transmittance. There is a procedure that we offer for calibrating the plate reader in order to relate its static light scattering measurements to nephelometric turbidity units, which are the standard units of turbidance. And so just another way that you can characterize your samples at different stages. You might use this to assess precipitation or solubility or other properties, opalescence. They are all well characterized using turbidance. And then last but not least, we have the microwell imaging. So there is an onboard camera, takes a view of the bottom of each well, so you can see what's happening in your well beyond the micro level and into the macro level. It's not a microscope, so you're not going to see 2-5 micron particles in here, but larger things that happen, whether it's sedimentation, decrease in transmittance due to turbidity, presence of a bubble that might have formed or been injected. These can all be assessed quickly, and the plate reader will take an image of each well as it makes the dynamic light scattering, static light scattering measurements, or you can tell it just to do it periodically in the course of a temperature ramp. So the dynamic light scattering, static light scattering plate reader is really an invaluable platform when you're engaged in developability studies and early stage formulation, looking at the prediction of stability, because it really scouts out a really significant section of the biophysical attribute landscape. It will give you accurate size and size distributions, determine the solution molecular weight, including aggregates, the rate of aggregation when you do an isothermal study, the propensity for aggregation or indicators of stability, such as the onset temperatures for size or molar mass change, as well as the colloidal stability indicators, KD and A2. And the nice thing about these is that they're really direct biophysical properties. There are other techniques out there which they're very definitely important, but they don't do a direct measurement of biophysical property. You get an indication, which may be a change in fluorescence or a change in heat capacity, that tell you something is going on, but they don't really tell you what's going on. When you make the measurements with light scattering, you know what's going on. You get a change in size, change in molecular weight, change in interactions. Those are all there for the taking. For high concentration proteins, assessments of solubility and viscosity. And finally, the macroscopic imaging of precipitants and other debris that might be in the well. You get a complete picture. The plate reader uses standard well plates, so probably well plates that you're using right now. They're inexpensive. They work with everything else that you're doing in terms of plate-based ecosystem. They're very convenient for whether for pipetting or using robotics and the full automation that is available with this type of measurement. Sample volume can be as low as 4 microliters if you so prefer, and could be as high as 150 or 200 microliters. So a very versatile system depending on which stage you're in terms of the formulation. The IR laser, 830 nanometers, there's no risk of it inducing aggregation. And new in the plate reader, we offer plate sealing using tape without condensation. I haven't shown it, but the software also offers a new user-friendly experiment design so that you can, in very short time, generate the standard methods that you're going to use to run through all these formulations and candidates. So I like to go a little bit beyond the details and look at the big picture. When you have high throughput screening with high throughput DLS and SLS, if you've been using SLS in cuvettes, DLS in cuvettes, there are some things you just can't do. You can't do 500 samples. You can't do all these long-term studies. But in the plate, you can carry out novel studies that you just couldn't do otherwise. You can be comprehensive, looking at dozens of samples, thousands of formulation temperature combinations, and get multiple biophysical attributes at the same time. You can be really productive. You can do weeks worth of cuvette-based DLS in just a couple of hours, and you'll get the picture. So you can analyze and visualize an entire data set at once using the spectral view heat map, and then zoom in for a detailed study of the most promising conditions, look at size, molecular weight, and KD and TM, and A2. And then you can get the even bigger picture. So because DLS is non-destructive, you can take the samples and just take that entire plate, transfer it to other analytical instruments, and the dynamic software will allow you to export your results in a single click. So all that information goes out to a spreadsheet type of file and then can be imported to your statistical analysis and reporting software. You can combine it with other data to get an even bigger picture. So with that, I thank you for your attention. And if you're interested in learning more about the DynaPro Plate Reader 3, I do invite you to the webpage wyatt.com/platereader, or just contact me. Thank you very much, and I am now open for questions.
Thank you very much, Dr. Sohm. We have lots of questions and not a lot of time, so let's get right to them. Our first question is from Natalia. How can the aggregates be quantified if they're not separated from the monomer?
Right. So when you do a separation like SEC mols, you get very accurate quantitation of the aggregates. It's not quite the same when you do it in plate. And so the kind of small aggregates like dimer and trimer and tetramer that you really separate well on SEC, you won't be able to separate. They're not discriminated in this technique. The molecular weight will give you an average, a weight average molar mass of the entire set of molecules, and the DLS will give you polydispersity. So basically, what is the range of sizes present? And that's the best you can do here for the small aggregates. For the larger aggregates, say the 100 nanometer aggregates, those don't show up in SEC. They're essentially caught up on the column. And dynamic light scattering does give you a measure of those aggregates. I would say it's semi-quantitative for the larger aggregates, not quite as quantitative as you might be thinking. Another option for quantifying or quantitating the larger aggregates, some called FFF mols. It's another separation technique with downstream light scattering.
All right. Our next question. How do you actually discriminate between good and undesirable data points? For example, the dust interference and so forth.
So the best way to learn how to do that is to attend DynaLSU, which is the Dynamic Light Scattering University that Wyatt offers to its customers. But there's a lot that goes into that. So essentially, we look first at the autocorrelation function. So the dynamic software lets you examine the autocorrelation function, see the quality of the fit, the parameters of the fit, and you get additional measurements called the sum of squares. And there are multiple properties that are presented in the software that allow you to do the filtering, and you can set the filter levels. So for instance, if you want to set the sum of squares for the not to go above a certain value, so basically not above a certain level of deviation, you can set that automatically, and it will allow you to filter those out automatically. And you also have an option for manual filtering just based on your own view of the function and of the various parameters that are presented.
Okay, perfect. Our next question, what is the concentration range that can be used for the plate?
So you can, first of all, the concentration range depends on the molecular weight of the protein, but let's focus on IgGs. Okay, so for IgGs, we have a minimum sensitivity for making a good measurement of size at 12.5 micrograms per milliliter. Okay. We have a minimum concentration for good measurement of molecular weight, which is about 0.4 milligrams per milliliter. And then you can keep going. So unless you get precipitation or issues with solubility, you can make measurements up in the range of 100 micrograms per milliliter, 100 milligrams per milliliter, 200 milligrams per milliliter. Now you can make good measurements. There are issues with data interpretation. That's a story that I could take another hour to describe. So that's the range. And then for other proteins, it's basically inversely proportional to molecular weight. So a smaller protein, you need higher concentrations.
All right. Next question. Could we use the DynaPlate Reader 3 to optimize buffer screens for protein complexes?
Sure. So because you're measuring the size of the protein and its molecular weight, if you have a buffer which leads to dissociation, you'll see that immediately in a change in size. So if the size changes, say from 5 nanometers in radius to 7 nanometers in radius, that's a pretty sharp change, and we see that very clearly. And you'll see that in the molecular weight as well. So the molecular weight might change from that of a monomer to that of a dimer, or that of the complex. Vice versa, if you have a buffer that causes additional complex formation, again, that will show up pretty readily in the change in size and molecular weight. So it is a good way for screening buffers for those complex formation.
All right. Is the instrument able to accurately determine KD on opalescent samples? The data quality and correlograms for these samples are difficult to interpret and don't trend with concentration consistently.
I wouldn't even attempt that because there's a conflict here, a conflict of interest, I'd say. If the sample is opalescent, it's it could be doing one of several different things to reach opalescence. It might be phase separation, it might be formation of fibrils, it could be doing all kinds of funny things, but all of those are deviations from the basic assumptions that go into the analysis of KD. So KD is assuming the point of the KD analysis is assuming that there's monomers with some degree of attraction or repulsion, but not the formation of phase-separated droplets or fibrils that can lead to opalescence. So they don't really go hand in hand.
Excellent. And looks like we have time for just one more question. We have, just to let you know, you'll be getting a long email, Dr. Sohm. We've got 2 pages of questions.
Well, we'll get back to everyone.
Okay, so here's our last one. What about excipients, sugars, and DLS measurements? How do they influence the measurement?
If the sugar is very clean, so that means that it has a hydrodynamic radius of about 0.1 or 0.2 nanometers. So it is well resolved from a protein, okay? What we've seen to some degree is that the addition of a sugar will cause a little bit of a polydispersity, just because if it's a high concentration, say 10-20% sugar, it does scatter light, and that will be picked up and will cause some deviations from, say, ideal measurements. If the sugar is not very clean, then there might actually be nanocrystals, and you'll pick those up as well. So it is important to make sure that you're using pharmaceutical grade sugars for that, and that they've been well filtered and well dissolved. Other than that, there are interesting interactions between sugar and protein, and you'll see certain deviations from the kind of expected behavior if both of them are at high concentrations. But if either one of them are at low concentrations, probably not too bad.
All right, perfect timing. With that, I'd like to thank Dr. Daniel Sohm from Wyatt Technology Corporation for your presentation today. I'd like to thank Wyatt for sponsoring our web symposia today. And most of all, I'd like to thank those of you who came and spent this hour with us. We know you have many places to be, and we're very grateful you chose to spend the time with us. Thank you all so much, and have a great day.